Hello everyone. So in this video we begin with chapter 16, Integral Calculus 2. So here are the learning objectives of this chapter. By the end of this chapter you should be familiar with first order differential equations, finding numerical solutions of differential equations using Euler's method, solving variable separable differential equations, solving homogeneous differential equations, solving linear differential equations, including the use of integrating factors, Maclaurin series to obtain expansions for e to the x, sine of x, cosine of x, natural logarithm of 1 plus x, and 1 plus x to the power of n, where n is a rational number. Simple substitution, products, integration, and differentiation to obtain other series. Maclaurin series developed from differential equations. So let's begin with section 16.1, differential equations. In general, a differential equation is an equation that contains an unknown function and one or more of its derivatives. The order of a differential equation is the order of the highest derivative that occurs in the equation. A first order differential equation is an equation that involves an unknown function and its first derivative. For example, when we consider any of the following differential equations. So derivative of y is equal to x to the 4, or derivative of y plus 2ty is equal to sine of t, or derivative of y is equal to y plus 2x, or the derivative of y in terms of t is equal to k times y. It is understood that y is an unknown function of x or t. So here are other examples. X times the derivative of y plus y times the derivative of y minus y is equal to 0. So this is a first order differential equation. Notice the notation here. F of xy derivative of y is equal to 0. Now this stands for the antiderivative. We will see this later on. This is the second derivative of y plus 3 times the first derivative of y minus 5y is equal to 0. This is a second order differential equation. Notice the difference in the notation. And then we have also the derivative of y in terms of t plus y times sine of t minus e to the power of cosine of t is equal to 0. This is a first order differential equation. In this case, instead of x, we have t as the variable. So now let's take a look at what a solution of a differential equation is. A function f is called a solution of a differential equation if the equation is satisfied for all values of x in some interval when y equals f of x and its derivatives are substituted into the equation. Thus, y equals f of x is equal to x minus 1 over x is a solution of x times derivative of y plus y is equal to 2x over the set of non-zero real numbers. So notice that here we find first the derivative of this function of y, and it's equal to 1 plus 1 over x squared. Then we substitute that back in here, and we're going to get x times the derivative of y, which is 1 plus 1 over x squared, plus x minus 1 over x, which is y that we see here. And then we solve for this, and notice that we get 2x. Thus, x derivative of y plus y is equal to 2x for all values over this interval. So now let's take a look at example 16.1. It says verify that y of x is equal to c, any constant c, times e to the power of x cubed is a solution to the differential equation derivative of y is equal to 3x squared y. So notice that here we would find the derivative of y. So it's just going to be dy over dx is equal to, remember that we would get the same value here for e to the power of x to the 3, but then we would have to do the chain rule and find the derivative for x cubed, which is 3x squared. So we would get 3x squared times c times e to the power of x cubed. And notice that this is the same as saying 3x squared times y. Therefore, it is a solution to the differential equation. Consequently, every function y of x of the form y of x equals c times e to the power of x cubed satisfies and thus is a solution of the given differential equation. Derivative of y is equal to 3x squared times y for all real x. In fact, y equals c times e to the power of x cubed defines an infinite family of different solutions to this differential equation, one for each choice of the arbitrary constant c, as shown in the diagram. So each one of these lines represents one of the functions in this family, and these vary only by whatever the value of c is. So now let's take a look at example 16.2. And it says, verify that y of x is equal to negative 1 over 2x to the 4 plus 3 is a solution to the differential equation derivative of y is equal to 8x cubed y squared. So first of all, notice that we can rewrite y of x as being equal to minus 2x to the 4 plus 3 to the power of negative 1. And then we can find the derivative of y. And this is going to equal negative 1 times minus 2x to the 4 plus 3 to the minus 2 times 8x to the power of 3. And then we can rewrite this as 8x cubed times 1 over 2x to the 4 plus 3 squared. Now notice that because this is squared, and although this will be positive from negative 1 multiplying the minus sign here, it doesn't really matter because it's squared, so we can just put a negative here and it would be a solution. Notice that this is the same as saying 8x cubed times y squared. So we continue with example 16.3. And it says, the solution of a differential equation is the initially unknown function y equals f of x, whose derivative is dy over dx. Find a solution to the differential equation, derivative of y is equal to 1 over x plus 1, where x cannot equal negative 1. So this is a case where they actually ask us to find the solution. So let's rewrite it over here. dy dx is equal to 1 over x plus 1. So what we do in these cases is that we separate the variables. Notice that this is a rate of change, which is a ratio, difference in y over difference in x. So notice that we can just rewrite this as dy is equal to 1 over x plus 1 dx. And then this allows us to integrate for both sides of the equation. So we integrate here in terms of y, and we integrate here in terms of x. So this is 1 times dy, which is going to be y, the integration of that, of course, right? And then remember that the solutions to these are in the form of a natural logarithm. So this would be natural logarithm of the absolute value of x plus 1 plus a constant c, where x cannot equal negative 1. Now don't forget to always use the constant. It's very important for these type of equations. So every solution of this equation is an antiderivative of 1 over x plus 1. So it's the integration of 1 over x plus 1 dx, which is in the form natural logarithm of x plus 1 plus c, where x cannot equal negative 1, as we found. So the solution of the differential equation is the explicitly defined function y equals natural logarithm of x plus 1, absolute value of x plus 1 plus c, where c is an arbitrary constant. This is called a general solution because it's not a single function, but an infinite family of functions dependent on the constant c. So the diagram to the right shows some members of the family of solutions. So this is when c is equal to -10, when c is equal to -5, when c is equal to 0, when c is equal to 5, when c is equal to 10, etc. So let's continue with other cases of separable differential equations, specifically example 16.4. And it says, find the general solution of the differential equation, derivative of y minus 9x squared y squared is equal to 5y squared. So instead of y prime, let's write the derivative as dy over dx, and let's rearrange. This equals 5y squared plus 9x squared y squared. So we need to separate the variables for x and y. We can do that here easily because we can just factor out the y squared. So notice that this is equal to y squared times 5 plus 9x squared. And then we can send this to the other side. We have 1 over y squared dy is equal to, and we send this to the other side, 5 plus 9x squared dx. Then we integrate both sides, to the left in terms of y, to the right in terms of x, and we're going to get -1 over y is equal to 5x plus 3x cubed plus a constant c. And then notice that this is the same as saying y is equal to -1 over 5x plus 3x cubed plus the arbitrary constant c. So let's continue with example 16.5. And it says, solve the differential equation, derivative of y is equal to 3x squared y over 1 plus 4y squared. So notice that we can rewrite this as dy over dx is equal to 3x squared times y over 1 plus 4y squared. And then we were able to separate the variables. So now we just have to send the y to the left and derivative of x to the right. And we would get 1 plus 4y squared over y dy is equal to 3x squared dx. And then this we can rewrite as 1 over y plus 4y dy is equal to 3x squared dx. And then we can integrate both sides. And here we're going to get the natural logarithm of the absolute value of y plus 2y squared is equal to x cubed plus c. So notice that in this case, we couldn't get an explicit solution. An explicit solution is when you have an answer in the form y equals function of x. And this is not the case here. So this is what is called an implicit solution. For every value of the arbitrary constant c, this defines an exact but implicit solution, y of x, as it cannot be written in the explicit form, y equals f of x. Some of the solution curves for a few values of c are shown in the diagram. So notice that they call them curves. Why is that? Well, because these are not functions. They wouldn't pass the horizontal line test. That is why it is said that the solution is in implicit form. So in the next slide, you're going to find some advice on how to solve equations by separation of variables. So the first piece of advice is to write the equation in the standard form, dy dx is equal to f of xy. Then you have to ask yourself, can we separate the variables? That is, can you rewrite dy dx is equal to a function of g of x times a function h of y? Or can you rewrite dy dx in the form p of x divided by q of y? If that is possible, then you can separate the variables to get dy over hy is equal to gx dx, or qy times dy is equal to px dx. Integrate both parts, right? So if you integrate both parts, and these are all the possible integrations that you can get. Evaluate the integrals if you can, and don't forget the arbitrary constant. Even though we have two integrals, one on the left and one on the right, we can combine both arbitrary constants into one. That's something I forgot to explain. And maybe you were wondering why there's only one c and not two c's on either side. And then finally, if possible, resolve the resulting equation with respect to y to get the equation in explicit form, y equals f of x. So now let's take a look at example 16.7, and it says, solve the initial value problem. Derivative of y is equal to y over x plus 1, where y1 is equal to 4. So this is the initial value, and this will allow us to solve for the arbitrary constant c. So take a look at this and notice that we can rearrange it as 1 over y dy is equal to 1 over x plus 1 dx. Then we integrate both sides of the equation. And on the left-hand side, we're going to get the natural logarithm of the absolute value of y is equal to the natural logarithm of the absolute value of x plus 1 plus c. And then using the properties of exponents and logarithms, we can just make this e to the power of that and e to the power of this. So this is going to give us absolute value of y is equal to Euler's number to the power of the natural logarithm of the absolute value of x plus 1, and we can separate this into times e to the power of c. But notice that this is just another constant, so we can substitute this with c. So let me erase it and substitute this with a simple c. And then now we can apply the properties of exponents and logarithms to this part. So we're going to get that the absolute value of y is equal to a constant c times the absolute value of x plus 1. And because we have an initial value, we know that when y is equal to 4, x is equal to 1. So we can rewrite this as the absolute value of 4 is equal to a constant c times 1 plus 1, which is 2, absolute value of 2. Then from here, we get that c is equal to 2. So then what we have now is absolute value of y is equal to 2 times the absolute value of x plus 1. But then using the properties of the absolute value, we know that this is the same as saying y is equal to plus minus 2 times x plus 1. So let's continue with example 16.9, and it says, solve the differential equation x dx plus Euler's number to the power of x plus y times cosine of y dy is equal to 0. So here we have to find a way to separate the variables. So notice that we can rewrite this as x dx plus e to the x times e to the y cosine of y dy is equal to 0. And then we can rewrite this as e to the y times cosine of y dy is equal to minus x dx divided by e to the x. And then we could just rewrite this as e to the y cosine of y dy is equal to minus e to the minus x dx. Then we integrate both sides. And then this is a case where you would have to use integration by parts. I recommend you do it as an exercise. And then you would get 1/2 e to the y times sine of y plus cosine of y is equal to e to the minus x times x plus 1 plus c. So now let's take a look at example 16.10. And it says, find the general solution of the population growth model. Difference in p over difference in time is equal to k times p. So this is the rate of change of a population with respect to time. So notice that we could simply rearrange the equation into the form 1 over p dp is equal to k dt. And then we integrate both sides, 1 with respect to population. So notice that k is just a constant multiplies p. It's a constant rate of change of the population. So we're going to get to the left natural logarithm of the absolute value of p is equal to kt, because we are doing the integration with respect to time here, right? Plus c. And then using the properties of exponents and logarithms, we're going to get that p, and here we don't have to worry about the absolute value because we're talking about positive, right? Population is always a positive number. And this is going to equal e to the power of c times e to the power of kt. But normally the notation for these population growth models is with a letter a instead of this. So we would write p is equal to a times e to the power of k times t. This is the general solution, and all solutions to this problem will be in this form. If the constant k is positive, the model describes population growth, as we can see here in figure 16.1, population growth. If it's negative, then it is decay, as you can see in figure 16.2. So this would represent exponential decay. If the population growth model in example 16.10 had the additional initial value that at t sub 0, the population is p sub 0, then this particular population satisfies the equation, and hence p sub 0 is equal to a times e to the power of kt sub 0. Therefore, a would be equal to p sub 0 divided by e to the power of kt sub 0, which is equal to p sub 0 times e to the power of minus kt sub 0. And the solution to the initial value problem is p is equal to a to the power of kt, which would be equal to p sub 0 times e to the power of minus kt sub 0 times e to the power of kt, and we end up with the expression p sub 0 times e to the power of k times t minus t sub 0. Notice that these are all just properties of exponents. There is a very important special case when t sub 0, or initial time, is equal to 0. The solution becomes p sub 0 times e to the power of kt. And this is the usual growth model that starts with t equals 0, or time equals 0, with the initial population p sub 0. So let's continue with example 16.11. And it says, a cold object is placed in a warmer medium that is kept at a constant temperature S. The rate of change of the temperature, T of T, so capital T is temperature, small t is time, with respect to time is proportional to the difference between the surrounding medium and the object, and hence it satisfies. So notice that here we have the rate of change of the temperature with respect to time is equal to K, which is a constant rate of change, of S minus T, where S is a constant temperature and T is the temperature of the object. And then we have that the initial temperature when time is 0 is T sub 0, where K, the constant K, is greater than 0, and the initial temperature, or T sub 0, is less than the surrounding medium. Find the solution to the initial value problem. Okay, so for this we're going to need a lot more space. So notice that we said that the rate of change of the temperature with respect to time is equal to a constant k times S minus T, which is the temperature of the medium minus the temperature of the object. And we have that when time is equal to 0, the temperature is T sub 0, or the initial temperature. So notice that we can rearrange this equation as difference in temperature is equal to K times the temperature of the medium minus the temperature of the object dt. And then from here, we can get difference in temperature over S minus T is equal to K dt. Then we integrate both sides of this equation, and from here, we're going to get negative natural logarithm of the absolute value of S minus T. And you might be wondering why negative? Well, because we have to do the derivative of this, and it's going to be -1. Therefore, to do the antiderivative, we need to put a negative sign in front of the integral, right? So this is going to equal kt plus a constant. Okay, then because we know that S, the temperature of the medium, is always going to be greater than the temperature of T, as we said initially, then we can just simply write this as the natural logarithm of S minus T is equal to minus kt minus an arbitrary constant. And then applying the properties of exponents and logarithms, we're going to get that S minus T is equal to e to the minus kt minus the arbitrary constant. But notice that we can rearrange this as T is equal to S minus e to the power of minus kt minus the arbitrary constant. So we need to solve for the initial value problem. We know that the initial temperature is taken into consideration when time is 0. So the initial temperature is going to equal S minus e to the power of minus k times 0 minus C1. Therefore, e to the power of minus C1 is equal to S minus the initial temperature. And then again, applying the properties of logarithms and exponents, we could get that minus C1 is equal to the natural logarithm of S minus the initial temperature. And that means that C1 is equal to minus the natural logarithm of S minus the initial temperature. Okay, so that means that we can plug this back into this part that we found before for C1. So if we do that, we're going to get that the natural logarithm of S minus T is equal to minus kt plus the natural logarithm of S minus T sub 0. And then we can rewrite this. Let's rewrite this over here. Notice that we can rewrite it as natural logarithm of S minus T minus the natural logarithm of S minus T sub 0 is equal to minus kt. And then from the properties of logarithms, we can rewrite this part to the left as the natural logarithm of s minus t divided by s minus t sub 0 equal to minus kt. And then again, using the properties of exponents and logarithms, we get s minus t over s minus t sub 0 is equal to e to the power of minus k times t. And then from here, we get that s minus t is equal to s minus t sub 0 times e to the minus kt. Therefore, minus t is equal to s minus t sub 0 e to the minus kt minus s. And finally, we get that t is equal to, and this is capital T, for temperature. So T is equal to S minus T sub 0 times e to the power of minus k times T. So notice this is the final equation. And what it means is that the temperature is going to equal the temperature of the medium minus the difference between the medium and the initial temperature times Euler's number to the power of minus k, which is the rate of change, times time. So now let's take a look at example 16.12, and it says the rate of decay of a substance Y at any time t is directly proportional to the amount of Y and also directly proportional to the amount of another substance X. The constant of proportionality is minus 1/2, and the value of X at any time t is given by X equals 4 over 1 minus t squared. So that means what they're saying really is that the rate of change of Y with respect to time is equal to minus 1/2 times 4 over 1 plus t squared times Y. Part A, given the initial condition that Y equals 10 when t equals 0, find Y as an explicit function of t. And part B, determine the amount of the substance remaining as t becomes very large. So in order to solve part B, we need to solve part A first. So we said that the rate of change of Y with respect to time is equal to minus 1/2 times 4 over 1 plus t squared, and this times Y. So we have to do a separation of variables, and here we're going to get dy over y is equal to minus 1/2 times 4 over 1 plus t squared dt. So now we integrate both sides, and we're going to get natural logarithm of y, because it's the amount of substance, so it's a positive number. We don't need to use absolute value. And this is going to equal, integrating the right-hand side, we're going to get 2 over 1 plus t, and then plus c, the constant. So applying the properties of exponents and logarithms, we're going to get that y is equal to Euler's number to the power of 2 over 1 plus t plus c. And from previous experience, we know that this is going to equal y equals a times e to the power of 2 divided by 1 plus t. And now we can solve for a. because at time 0, the amount is 10. So 10 is equal to A times E squared. Then from here, we're going to get that A is equal to 10 over E squared, which is the same as 10 times E to the minus 2. So that means that our function is going to be y equals 10 times E to the minus 2 times E to the power of 2 over 1 plus t. And then from the properties of exponents, we will get that y is equal to e to the power of minus 2t over 1 plus t. So that would be the equation. Now, notice that this here, this exponent, is the result of adding minus 2 plus 2 over 1 plus t. So for part B, what is the limit as t becomes infinite? So really what we need to look at is at the exponent part. So what happens to the expression minus 2t over 1 plus t as t approaches infinity? From the rules of limits, we know that this is going to have a limit of negative 2. So that means that it's going to tend, the equation itself is going to tend to y equals e to the minus 2, which is approximately 1.36, and that is to 3 significant figures. So next we're going to look at logistic differential equations. Example 16.10 looked at the population growth model. In that model, we use the fact that the rate of change of a variable y, p in the example, is proportional to the value of y. We observed that the differential equation in the form the change of y with respect to time is equal to k times y, and found that the general solution was y equals a times e to the power of kt. Now, exponential growth is unlimited and does not provide an accurate model for the growth of a population over a long period of time. To obtain a more realistic model, we need to take into account the fact that as the population increases, quite a few factors will begin to affect the growth rate. For example, there will be increased competition for the limited resources that are available, increases in disease, and overcrowding of the limited available space, all of which would serve to slow the growth rate. In order to model this situation mathematically, we amend the differential equation leading to the modest exponential growth law we introduced by addition of a term that slows the growth down as the population increases. If we consider a closed environment, neglecting factors such as immigration and emigration, then the rate of change of population can be modeled by the differential equation dy over dt is equal to b minus d times y, where b and d denote the birth and death rates. In a more general situation, the increased competition as the population grows will result in a corresponding increase in the death rate. One way to take this into account is to assume that the death rate is directly proportional to the present population, and that the birth rate remains constant. The resulting initial value problem leading to the population growth can now be written as dy dt is equal to initial birth rate minus initial death rate times y, and that times y, where b sub 0 and d sub 0 are positive constants representing specific birth and death rates. It is useful to write the differential equation in the equivalent form dy over dt is equal to k times 1 minus y over L times y, where k is equal to b sub 0 and L is equal to b sub 0 over d sub 0. So you might be wondering, where the hell did this come from? Well, notice that we can rewrite this here as, let's write it as b sub 0 minus b sub 0 over b sub 0 times d sub 0 times y, and that times y. Then we can factor out b sub 0, and notice that we could write it as b sub 0 times 1 minus d sub 0 over b sub 0 times y, and this times y. And then this is the same as writing it as b sub 0 times 1 minus y over b sub 0 over d sub 0, and this times y. So notice that when you do the substitution, k equals b sub 0 and L equals b sub 0 over d sub 0, you get this expression for formula 1, or equation 1. Equation 1 is called the logistic equation, and the corresponding population model is called the logistic model. The differential equation 1 is separable and can be solved without difficulty. The constant L is called the carrying capacity of the population, and the graph of function y is called the logistic curve, which can be seen here in figure 16.5. So notice how initially the growth rate is exponential, and then as it reaches the value L, which is the carrying capacity, it starts to remain at that level. So now let's focus on example 16.14, and it says, solve the logistic differential equation dy over dt is equal to ky times 1 minus y over L. So here we proceed as usual with the separation of variables. So notice that we can rewrite this as dy over y times 1 minus y over L is equal to k dt. So on the right-hand side, we integrate with respect to time, and on the left-hand side, we integrate with respect to y. So notice that if we rearrange the expression on the left-hand side, we can write it as the integration of 1 over y plus 1 over L minus y dy, and that would be the result of applying partial fractions to this expression. And then on the right-hand side, it remains the same. And now integrating this, we're going to get the natural logarithm of the absolute value of y minus the natural logarithm of L minus y, absolute value of that, is equal to k times t plus c. Now, the thing is that we need to solve for y, so we are going to rearrange this equation into this other expression. So it's going to be natural logarithm of the absolute value of L minus y minus the natural logarithm of the absolute value of y is now going to equal minus kt minus c. And the reason is that we want to rearrange this so that we get natural logarithm of L minus y over y, absolute value of that, is equal to minus kt minus c. So then if we apply the properties again of logarithms and exponential functions, this expression is going to end up being L minus y over y is equal to Euler's number to the power of minus c times Euler's number to the power of minus kt. And then we can just express this, instead of using this e to the minus c, we're going to use a random variable b. It could also be A or C or any of the latter, right? But we want to use B in this case. So notice that from here, we can send this y to multiply. So rearranging again, we would get L minus y is equal to y times B Euler's number to the minus kt. And then this we can rewrite as L equals y times B times e to the minus kt plus y. And then if we factor out the y, this is going to be L equals y times B, Euler's number to the minus kt, plus 1. And then finally we get that y is equal to L divided by 1 plus B, which is the arbitrary constant, e to the power of minus kt. So this is the family of equations that solve the logistic differential equation that we saw. So now let's continue with example 16.15. It says an official wildlife commission releases 20 deer into a protected forest. After 5 years, the deer population is 208. The commission believes that the environment cannot support more than 400 deer. Notice that this is the carrying capacity. Part A, write a model for the deer population in terms of the number of years t. So for part A, let's take into account that the rate of change of the deer population is going to equal some constant k times p times 1 minus p over the carrying capacity, which is 400, where p is going to be a number between 20 and 400. From the previous example, we know that the solution to this type of problem is going to be in the form P equals L, in this case 400, over 1 plus an arbitrary constant B times e to the minus kt. So in order to find the model that we want, we need to solve for B and we need to solve for the rate of change k. But we know that at time 0, the population was 20. So that means, that implies that 20 is equal to 400 over 1 plus b. And then from here we get that 20 plus 20b is equal to 400. And then if we solve for this, we're going to get that b is equal to 19. Then we also know that after 5 years, we can see that here, after 5 years, the deer population is 208. So that means that P of 5 is 208. So with this, we can find the constant K. Just by solving the equation, 208 is equal to 400 over 1 plus 19 e to the power of minus k times 5. And then if we solve for k, you're going to get that k is approximately 0.6049. And we're going to carry one more decimal just for the sake of being as accurate as possible. So then we would have the model for this particular case. It's going to be P is equal to 400 divided by 1 plus 19 times e to the power of minus, notice that we have to take into account this minus here, minus 0.6049 t. For part B, it says use the model to estimate the deer population after 10 years. So that simply means plug 10 in here, right? And then from that, we're going to get that P is approximately 383. Notice that for these questions, you want to answer in whole numbers because we're talking about population. So that's the approximate size of the deer population. So let's write here deer. For part C, it says discuss the long-term trend of the deer population. So I'll do it here on the top left. The long-term trend is what happens to the limit of P of the population as t tends to infinity. And we know that that means what is the limit as t tends to infinity for our model, right? 400 over 1 plus 19e to the power of minus 0.6049 t. And this is just going to be 400, which is the carrying capacity anyway. But notice that this here, as t gets greater and greater, Euler's number gets closer and closer to 0. So this tends to 0. And then we're going to get 400 divided by 1, which is 400. That's why the logistic curve has the shape that we saw previously. So next we're going to look at homogeneous differential equations. Some differential equations that are not separable in x and y can be made separable by a change of variables. This is true for differential equations of the form derivative of y is equal to f of xy, where f is a homogeneous function. The function given by f of x, y is homogeneous of degree n if f of t times x, t times y is equal to t to the n f of x, y, where n is an integer. So this is a lot easier than what it sounds. So notice that if you rewrite every x and every y, for example here, if you rewrite every x and every y as xt or yt, we get this other expression. So 2x squared y minus 5x cubed plus 7xy squared is homogeneous of degree 3, because notice that if you, again, substitute x by tx and y by ty, you're going to get an expression where you can factor out t cubed, and it's in the form t cubed f of xy. F of xy is equal to 2x squared y minus 5x squared y squared plus 7xy is not homogeneous because you will not get an expression in this desired form by substituting x and y by tx and ty. Now, this third one here, separating the variables, is easy. And this is what is considered a homogeneous function of degree 0, because you could re-express it as t of 0 times x over y, or in that form. So now we're going to take a look at example 16.16, and it says solve the differential equation xy derivative of y is equal to 3x squared plus y squared. So notice that we can rewrite this as difference in y over difference in x is equal to 3x squared plus y squared divided by xy. And indeed, this is homogeneous because notice that we can rewrite this as 3 times tx squared plus ty squared over tx times ty. And this is obviously in the form t squared of f of xy. So the trick here is to do a substitution. So we're going to substitute y, we're going to substitute for v times x. And notice then the derivative of y is going to equal, and this is applying the product rule, v times the derivative of x plus x times the derivative of v. So now we proceed to substitute y and derivative of y in the original differential equation. So this is now going to be v dx plus x dv over dx is equal to 3x squared plus v squared x squared. And this over x times vx. So that's going to be x squared v. And then in this expression to the right, we're going to get 3 plus v squared over v. So continuing over here, we're going to send the v to multiply the left-hand side. So we're going to get v squared dx plus xv dv is equal to, and this is from sending dx to multiply the right-hand side, we're going to get 3 dx plus v squared dx. So notice that this and this will cancel out, and now we can separate these further, separate the variables, and we're going to get that v dv is equal to 3 over x dx. So now it's just a matter of integrating these two expressions, and then from here we're going to get that v squared over 2 is equal to 3 times the natural logarithm of the absolute value of x plus a constant c. Then we send the two to multiply, and we're going to get that v squared is equal to 6 times the natural logarithm of x plus 2 times c. Now, if we substitute the original expression for v, notice that here we have that y is equal to vx. Therefore, v is equal to y over x. So plugging that in here, we're going to get y squared over x squared is equal to 6 natural logarithm of absolute value of x plus 2c. And then we're going to get the implicit form or the implicit form of a solution, which is y squared is equal to x squared times 6 natural logarithm of the absolute value of x plus 2c. So now we're going to do example 16.17, which will be the last one on this video. And it says, find the general solution of x squared minus y squared dx plus 3xy dy is equal to 0. So let's recall that the substitutions we need to do are for y, which is equal to v times x, and then the derivative of y, which is equal to v dx plus x dv. So now let's do the substitution in the original differential equation. And we're going to get x squared minus v squared x squared dx plus 3 vx squared times dy, which we said is v dx plus x dv, and this equals 0. So now we're going to expand this, and we're going to get the expression x squared dx minus v squared x squared dx plus 3v squared x squared dx plus 3 vx cubed dv, and this equals 0. Continuing over here, notice that we can simplify because this and this are similar terms. So this is going to simplify a bit into x squared dx plus 2 v squared x squared dx plus 3 vx cubed dv is equal to 0. And then next we're going to factor out in this expression. Notice that we can factor out x squared and dx. So we can write it as x squared times dx times 1 plus 2 v squared. And we'll send this expression to the other side, is equal to minus 3v x cubed dv. And now we can send this x cubed to the other side, the left-hand side, and this expression we can send to divide to the right-hand side. So now we're going to get 1 over x dx is equal to minus 3v over 1 plus 2v squared dv. Okay, so next we integrate both sides, and the expression on the left-hand side is simply going to be the natural logarithm of the absolute value of x, and on the right-hand side we should get minus 3/4 times the natural logarithm of 1 plus 2v squared. Notice that we don't use absolute value here because this is always going to be positive, plus a constant. Okay, so now we are going to use the properties of logarithms. But first, notice that we can rewrite this as 4 times c1 over 4, and that will allow us to send this 4 to multiply to the other side. So we get the expression 4 times the natural logarithm of the absolute value of x is equal to minus 3 natural logarithm of 1 plus 2v squared plus 4 times c1. Now let's do another substitution. Let 4 times c1 equal the natural logarithm of c. Now this is just to take advantage of the convenience of the properties of natural logarithms. So notice that now we can rewrite this as the natural logarithm of x to the 4 from the properties of logarithms is equal to the natural logarithm of 1 plus 2v squared to the negative 3 plus the natural logarithm of c. But this expression on the right-hand side is equal to the natural logarithm of c times 1 plus 2v squared to the minus 3. So now, using Euler's number on both sides of this expression, we're going to get that x to the 4 is equal to c times 1 plus 2, and now we're going to substitute for v. Remember that v is the same as y over x, so 2 times y squared over x squared, and this to the power of negative 3. We can rewrite this as x to the 4 is equal to c times x squared plus 2y squared over x squared. That's just adding these fractions to the power of negative 3. Now, rearranging, we get that c is equal to x to the 4 times x squared plus 2y squared over x squared, but now to the power of positive 3 because we sent it to the other side to divide. And then we can also take out this x in the form of x to the 6. So we're going to get c is equal to 1 over x squared times x squared plus 2y squared to the power of 3. And then we can leave it in its implicit form as cx squared is equal to x squared plus 2y squared, and this cubed.